Hey everyone, welcome back to Chem Story. Hope you're all doing well. Today we're diving into something that's fundamental, but also super useful when it comes to acids and bases. We're talking about their relative strength. Understanding this helps us predict which direction a reaction will go, compare how acidic different compounds are, and explain why some acids are just stronger than others. So let's break it down step by step. First, let's talk about the relationship between acids and their conjugate bases. There's a general trend we see. The stronger the acid, the weaker its conjugate base. And the weaker the acid, the stronger its conjugate base. Why is that? Well, strong acids give up protons easily, so their conjugate bases don't really feel the need to grab those protons back. But weak acids tend to hold onto their protons more tightly, which means their conjugate bases are more likely to accept a proton when the chance comes up. So what actually happens when an acid gives up a proton? The species that's left behind, its conjugate base, now has to deal with that extra negative charge. If the acid was strong, its conjugate base is usually pretty stable. It doesn't really have any strong desire to grab a proton again, and that's why it's weak. But if the acid was weak, its conjugate base isn't all that stable. It's much more eager to accept a proton, which makes it a stronger base. And the same logic works the other way around too, for bases and their conjugate acids. This kind of inverse relationship is super important. It helps us understand how acids and bases behave, especially when we're looking at reaction equilibria. Let's look at some examples. Strong acids like HCl have very weak conjugate bases, such as Cl-. On the other hand, weak acids like ammonia, NH3, have much stronger conjugate bases, like NH2-. To compare different acids, we can use a table that lists their pKa values along with their conjugate bases. And here's an important rule to remember. The lower the pKa, the stronger the acid. Now that we've talked about acid and base strength, let's see how this actually plays out in real reactions. Here's a simple rule. Acid-base reactions always move toward the more stable side. In other words, the system naturally shifts toward forming the weaker acid and the weaker base. So if you want to predict which direction a reaction will go, just compare the pKa values. If the pKa of the conjugate acid is significantly higher than that of the reactant acid, the forward reaction is favored. For example, acetylene, C2H2, has a pKa around 25, and its conjugate base, NH2-, has a conjugate acid, NH3, with a pKa around 38. Since NH3 is the weaker acid, the forward reaction is favored. Now let's compare acetylene with the ethoxide ion. The conjugate acid of ethoxide ion is ethanol, and it has a pKa around 16. That's quite a bit lower than the pKa of acetylene, which is around 25. So in this case, the equilibrium shifts toward acetylene, meaning the reverse reaction is favored. And that's the beauty of pKa values. By simply comparing them, we can quickly figure out which direction an acid-base reaction will go. Now let's talk about what actually makes an acid stronger or weaker. There are a few key factors we look at when comparing acidity. First, the size of the partial positive charge, the delta plus on the acidic hydrogen, plays a role. A larger delta plus means the proton is easier to lose, and that makes the acid stronger. Another really important factor is the stability of the conjugate base. And one of the biggest things that affects that stability is how reactive the conjugate base is and how much electron density it's holding onto. Acid and base strength are really closely tied to the properties of their conjugate pairs. And here's the key idea. The strength of the conjugate base tells us a lot about how strong or weak the original acid is. If the conjugate base has high electron density and is highly reactive, that means it really wants to grab a proton, which makes it a strong base. And since strong bases come from weak acids, that tells us the original acid wasn't very strong to begin with. But if the conjugate base has low electron density and isn't very reactive, it's a weak base, meaning it doesn't have a strong pull for protons. And that suggests the original acid was strong because it gave up its proton easily and left behind a nice, stable conjugate base. So in short, a strong conjugate base means the acid was weak, and a weak conjugate base means the acid was strong. Now let's talk about what actually makes an acid strong or weak. One of the biggest factors is what we call the elemental effect. This depends on the nature of the atom that's directly bonded to hydrogen. We'll just call that atom A in the HA bond. And when we're thinking about A, there are four main things we want to consider: its charge, its electronegativity, its atomic size, and its hybridization. First, let's start with charge. If atom A has a positive charge, it pulls electron density away from the hydrogen, and that makes it easier for the hydrogen to leave as a proton. So in general, the higher the positive charge, the stronger the acidity. A great example is H3O+ versus H2O. Since H3O+ has an extra positive charge on oxygen, it's much more acidic than neutral H2O. Same goes for NH4+ and NH3. The positive charge on nitrogen in NH4+ weakens the NH bond, which makes it easier for the proton to break away, and that means stronger acidity. Next, we have electronegativity. As we move across a period from left to right on the periodic table, electronegativity increases. That means the atom pulls electrons more strongly, and that weakens the HA bond. When that bond is weaker, it's easier for hydrogen to leave as H+, and that makes the acid stronger. Let's walk through an example using CH4, NH3, H2O, and HF. CH4, or methane, isn't acidic at all, because carbon doesn't pull electrons strongly. That makes the CH bond very stable, and it's super hard to lose a proton. NH3, or ammonia, is a little more acidic than methane, because nitrogen is more electronegative than carbon, but still, it's not enough to make it a strong acid. H2O is even more acidic, because oxygen is more electronegative than nitrogen. It pulls electron density away from hydrogen more effectively, weakening the OH bond and making it easier for the proton to come off. Then we get to HF hydrofluoric acid, which is the strongest in this trend. Fluorine is the most electronegative of all, so it creates the weakest HF bond, and that makes it super easy to lose H+. Now let's talk about atomic size. As we move down a group, from top to bottom on the periodic table, atoms get bigger, and as atomic size increases, acidity also increases. Why is that? Because larger atoms form weaker HA bonds, and when the bond is weak, it's easier for the hydrogen to break off as a proton. A great example is the trend in hydrogen halides: HF, HCl, HBr, and HI. HF is the weakest acid in this group, and HI is the strongest. That's because iodine is the largest atom here, and the HI bond is much weaker than the HF bond. It breaks more easily, so H+ can dissociate more readily, and that makes HI the strongest acid in the series. We see the same trend when we compare water and hydrogen sulfide, or an alcohol and a thiol. Sulfur is larger than oxygen, so the HS bond is weaker than the HO bond. And because of that, it's easier for sulfur to let go of a proton. That's why hydrogen sulfide is more acidic than water, and a thiol is more acidic than an alcohol. Finally, let's talk about hybridization. The more S character an atom has, the closer its electrons are held to the nucleus. And when electrons are closer to the nucleus, the conjugate base is more stable, which makes the acid stronger. Let's look at some carbon-hydrogen bonds to see how this works. Acetylene, which is sp hybridized and has about 50% S character, is the most acidic. That higher S character means the electrons are held tighter to the nucleus, and that helps stabilize the conjugate base. Ethene is sp2 hybridized with about 33% S character. It's less acidic than acetylene because the electrons are a little farther from the nucleus, so the conjugate base isn't quite as stable. Then we have ethane, which is sp3 hybridized and has only 25% S character. That means the electrons are held the farthest from the nucleus, making the conjugate base the least stable, and that's why ethane is the least acidic of the three. Now let's talk about the inductive effect. This refers to how atoms can donate or withdraw electron density through sigma bonds. Electronegative atoms, like fluorine or chlorine, tend to pull electron density away from nearby atoms, and when that happens, it helps stabilize the conjugate base. A more stable conjugate base means a stronger acid. For example, let's say there's an electronegative atom, like fluorine or chlorine, near the acidic proton. These atoms pull electron density away, which helps stabilize the conjugate base. And the result? Increased acidity. But here's something important. This effect weakens as the distance increases. The farther that electronegative atom is from the acidic site, the less impact it has. So when you're comparing acidity, don't just look at whether electronegative atoms are present. Also check how close they are to the acidic hydrogen. You'll see this trend really clearly when you look at the pKa values of different compounds based on these factors. Now, let's move on to resonance stabilization, another key factor that affects acid strength. If a conjugate base can spread out its negative charge through resonance, it becomes more stable. And when the conjugate base is more stable, the original acid becomes stronger. A great example is acetic acid, compared to ethanol. Acetic acid is much more acidic because its conjugate base, acetate, can delocalize the negative charge between the two oxygen atoms. That resonance makes it much more stable. On the other hand, ethanol's conjugate base, ethoxide, doesn't have any resonance stabilization, so it stays localized and unstable. That's why ethanol is a much weaker acid. We see a similar trend when we compare phenol and methanol. The conjugate base of phenol, phenoxide, can spread out its negative charge across the benzene ring, which gives it extra stability. But methanol's conjugate base, methoxide, doesn't have any resonance at all, so it's less stable, and methanol ends up being a much weaker acid. Now, let's take a look at aromaticity, a unique concept that can have a powerful effect on acidity. If the conjugate base of an acid is aromatic, it gains a significant amount of stability. To be aromatic, it has to follow Huckel's rule, which means it must have 4n plus 2 pi electrons in a planar cyclic, fully conjugated system. When a conjugate base meets those conditions and becomes aromatic, it gets a big boost in stability, and as a result, the original acid becomes much stronger. So in certain cases, aromaticity alone can dramatically increase acidity, even if the structure doesn't contain highly electronegative atoms or traditional resonance. A great example of this is cyclopentadiene. At first glance, it just looks like a regular hydrocarbon, nothing too special. But surprisingly, its pKa is around 16, which is way lower than you'd expect for a compound that doesn't even have an oxygen atom. So what's going on here? The key is its conjugate base, the cyclopentadienyl anion. It's aromatic, and that aromaticity makes it extremely stable. This extra stability greatly enhances the acidity of cyclopentadiene, especially when you compare it to similar compounds that don't have aromatic stabilization. In other words, if losing a proton makes the conjugate base aromatic, then the acid will be much stronger than you'd expect. That's all for now. Thanks for watching, and I'll see you in the next lesson.